our emphasis that I tend to take, which is focusing on what the secular side of things says about the world around us and the universe around us, and what we can learn from that. It's often portrayed that the creation issue is this war of science versus religion, that we look at everything through this religious perspective, but the scientists all have this different perspective. And if we weren't blinded by our preconceptions, by our pre-commitment to the Bible as being true, then surely we would see that their side is the better interpretation of the things. And when I speak, I like to start by beginning and noting that I'm one of many for whom the opposite was true. I became a creationist before I became a Christian. I was an atheist until my late 20s, working as an engineer in the military space program. When I was confronted with, and I was an atheist and an evolutionist, that's how I went into that program. When I was confronted with evidence that my atheism and evolutionism were contrary to the universe around us, and that was not a short process of reevaluating my beliefs, but over the better part of a year I came to realize that my evolutionism, my atheism did not match the cosmos. And that led to a bit of a personal crisis for me because I didn't especially want the Bible to be true. I understood very well what the Bible had to say about me as a sinner and what the fate that sinners get if they are not forgiven for those sins. But eventually, after having become convinced of creation, I then became a Christian. And I mentioned that briefly only to make the point, I'm one of many for whom we're not creationists because we're blinded by our faith in the Bible. Many of us were persuaded by the evidence first and then became Christians afterward. Now, creation is not sufficient to make you a Christian, of course. That's the work of the Holy Spirit. I mean, there are many Muslims who are creationists, for example. But again, this is not a war of science versus religion. And the point of my talk here tonight is to show you that the evidence that is claimed to present this secular history of things actually doesn't support a secular history very well at all. In fact, when you take it to its logical conclusion, you wind up in a place where the atheists really don't want to go. And that's what we'll see tonight. So as you can see, the title of the talk is Our Created Universe. Now, when we see the universe around us, the question is, well, how did it get there? Well, there's two basic interpretations. It was either created by someone or it got there by itself somehow. Now, there's, of course, varieties within those two camps. But for our purposes tonight, of course, we're talking about the creationist perspective from the Bible, and the Bible says, in the beginning, God created the heavens and the earth. And most of us are familiar with that verse. But we're told that it's illegitimate to use the Bible to interpret the universe we see around us. Well, why is that? Well, because the Bible is a work describing a supernatural act of creation. And the prefix super just means above or beyond. So that which is supernatural is that which is above or beyond the natural world. And we're told that it's illegitimate, it's not allowed to use supernatural explanations in science. Instead, we're told that the only allowable perspective is naturalism. And I believe Chris used that word in his introduction. Naturalism is just the idea that only natural processes that we see going on right now around us, only those processes are allowed to be used to explain past history. So the overall naturalistic worldview looks something like this. Here's a timeline. In the very beginning, there was a Big Bang, roughly 13.8 billion years ago. From that Big Bang, formed a lot of gas, mostly hydrogen, about 3/4 hydrogen, 1/4 helium, give or take. From that gas, stars were formed. Some of those stars gathered themselves into galaxies over time, one of which is our own Milky Way. Within the Milky Way galaxy, about 4.5 billion years ago, formed another cloud of gas. Within that, planets formed, and this became our solar system. And of course, one of those planets is the planet Earth, where we are today, looking at it all. Now, both sides of this creation versus evolution discussion would agree that we are indeed here on the Earth looking at it today. But what about this earlier part of the timeline? Well, we can go through each of these stages and discuss them each in depth. My purpose tonight is to not do that in depth in each stage, because that would take too long, that much more time than we have. But we'll look at a little bit of an overview, and we'll start with the most recent part of this model, which is here, the origin of our solar system. Now, what we're being told in the science media and so on is that 4.5 or so billion years ago, there was a swirling cloud of gas, and within that cloud of gas, little dust particles started to condense. The dust particles started to stick together to become little rocks. The little rocks started to stick together to become big rocks. The big rocks stuck together to become bigger rocks, which stuck together to become planetesimals, or asteroids. The word planetesimal means little planets. And then those stuck together, these asteroids or planetesimals stuck together, to become the planets that we see today. Now, this is what the science media and textbooks and everything else will tell you actually happened, but the minor detail in this model is that it doesn't actually work. You can't get planetesimals starting from grains of dust. One of my astrophysics textbooks points out that once these planetesimals have been formed, further growth of planets may occur through their gravitational accretion, they're sticking together by gravity, into large bodies, but just how that takes place is not understood. See, the problem is when these objects are still small, they don't have much mass yet, so their gravitational attraction to each other is not yet enough to overcome more destructive forces like the rocks smashing together and breaking them into more pieces rather than building up into larger bodies. So you can get dust stuck together to become little rocks, and you can get big planetesimals to gather together to form larger bodies like planets, but that middle stage of the process where you get from the small rocks to the big rocks, there's a big gap there, and the physics says you don't get the larger things, which is why you see quotes like this one. The formation of planetesimals, the kilometer-sized planetary precursors, is still a puzzling process. By the way, I'll be quoting a lot of people here in my presentation tonight, and unless otherwise noted, they are all secular authors. They're not creationists, they're not, to my knowledge, any of them Christians. So I like doing this to show you in their own words what their models actually say. How the first stage of this process, primary accretion, works is a fundamental unsolved problem of planetary science. Well, yeah, this is pretty fundamental because these are the building blocks that all the other planets are supposed to have come from. I mean, this is the foundational part of the model right here. If you don't fix this, you don't have a model from that point on. Now, this problem has been around for actually quite a while, and they've been scratching their heads over it the whole time because the problems here are pretty basic. Probably the only real solution that's being bandied about right now is this one. Objects must have grown very rapidly from sub-meter-sized pebbles into 100-kilometer-sized bodies, possibly in a single leap. What does that mean? Well, that means rocks this big turned into asteroids the size of Rhode Island without passing through any size in the middle. Now, is that a scientific model? Or is that just a hand-waving excuse? So, well, it must have went from here to there, even though the science, the physics in the middle says it can't have done that. Therefore, it just leapt over that gap. Really? Well, I don't think that's how it works. We'll set that aside for now, though, and look at the solar system overall. Consists of 8, not 9, planets. Sorry, Pluto got demoted. And these are the planets roughly to scale with each other and the sun, although not in their distance. In real life, these things are much farther away from each other and from the sun than you see here. But this is a pretty good idea of their relative size. So that little dot there is Mercury, smaller than my laser pointer actually. Then there's Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and some other riffraff like asteroids and Pluto. Now, we could actually go through each planet in the solar system and show how each one discredits that secular model of origins in a different way, and I think that talk is a lot of fun. Tonight, though, I'll limit my comments to just a few of the planets. The first 4 planets are called terrestrial planets because they're rocky like Earth is. So here's Earth, and here's Mercury, Venus, and Mars. And they're all roughly composed of the same rocky material as Earth, thus they're called terrestrial planets. The next 4 out there are all called gas giants, and you can see how small Earth is relative to these. These are some very large objects indeed. So the largest of the planets in the solar system is Jupiter. And Jupiter, of course, is famous for its giant red spot, great red spot. This thing here, which is a storm system bigger than the entire Earth. And it's been there for as long as we've had telescopes to look at it, for several hundred years now. So for all we know, it's been there since the planet was created. Now, if you want to have a planet this big, you need a whole lot of stuff in your model to create such a thing. But remember, the secular model can't actually produce the planetesimals to make this thing. As this quote says, how this process continues from meter-sized boulders, remember, the rocks they only get to this big and then they stop growing, to kilometer-scale planetesimals is a major unsolved problem. Boulders are expected to stick together poorly, like I already told you, and to spiral into the protostar in a few hundred orbits owing to a headwind from the slower rotating gas. Here's a second problem with the planetesimals that I didn't tell you about yet. Not only do you not get the boulders sticking together to make bigger rocks, as they're going around the protostar, i.e. the sun that's forming in the middle, as it's going through this cloud of gas, the effect is similar to trying to swim through molasses. If you swim through molasses, does it help you go fast, or does it slow you down? It slows you down, of course, right? Well, if a burgeoning asteroid is going through this cloud of gas as it goes around the sun, same sort of thing. As it's plowing through this material, it's slowing down. It's kind of the headwind. Well, the way an orbit works is when you slow down, you move inwards. And so notice what this says here. These rocks will spiral into the protostar, i.e. crash into the sun, in just a few hundred orbits. That's just a few hundred years. Very short amount of time relative to the billions of years that are supposedly at play here. So not only can the rocks not build past a certain size, even if you do get rocks, they're still going to spiral all the way into the sun and crash into the sun, merge into it, and not make planets. So when you look at planets at this scale, you don't have the building blocks to make any in the secular model. In addition to that, there's also chemical problems explaining how the rocks that should have formed out of Jupiter's neighborhood could have formed the planet. Jupiter's chemical composition doesn't match the secular model in some ways. But overall, you ask the question, where did Jupiter come from? As this article in a science journal noted, Jupiter is the largest of all the planets, but results in Nature, scientific journal by that name, now reveal the embarrassing fact that we know next to nothing about how or where it formed. This other author said this, "I don't think the existence of Jupiter would be predicted if it weren't observed." And by the way, that problem of spiraling into the sun doesn't only apply to planetesimals, it also applies to planets, because they're going to be moving through that same material also. Jupiter, it turns out, has what's called a migration problem, meaning it would have migrated, moved inwards, all the way into the sun. As this article points out, theories predict that the giant protoplanets, i.e. the planets that are forming, will merge into the central star, in other words, crash into the sun, before planets have time to form. This makes it very difficult to understand how they can form at all. Understanding the formation of giant planets is currently one of the major challenges for astronomers. In other words, we see Jupiter, but the model says we shouldn't be there, yet there it is. There's more we could say about Jupiter if we had the time, but for tonight, let's move on to the next planet outwards in the solar system, which is Saturn. Saturn, of course, is famous for its beautiful rings. Saturn also suffers from the migration problem, just like Jupiter does. It, too, should have moved all the way into the sun and crashed into it before it had time to finish forming. So not only should Jupiter not be there, Saturn shouldn't be there either, according to the secular model. There's more we could say about that planet if we had more time, but tonight I want to mention a couple of its moons. One of Saturn's moons is called Enceladus. It's a pretty little moon, as you can see. And the lighting up here may be kind of hard for this. This is a photograph of Enceladus. This is Saturn's rings, and the spacecraft that took this was almost edge-on to the rings as it did that. You may be able to notice a little smudge beneath Enceladus there. Well, when we took close-up photographs, we saw this. Enceladus has water geysers, water and ice geysers actually, coming out of its south pole. That's what all this material is. And here's a false color picture to show you how large these geysers are. There's a tremendous amount of material coming out of here. Now this is interesting because Enceladus is supposed to be too old, quote unquote, billions of years old, and therefore should have cooled off after its formation long ago. This is not a very big moon here. It shouldn't have the energy to be geologically active still, if it were actually billions of years old. Yet it is geologically active. So on the face of it, that would seem to indicate it's not actually billions of years old, and wouldn't actually fit the secular model then. Now, there are some attempts to justify some of this activity because Enceladus can get energy from tidal flexing from its neighbors in Saturn, and that's true, it can get some, but it can't get enough to account for what we see going on here. One of Saturn's other moons is called Titan, and Titan, of course, is a very large moon, as you gather by its name. It's actually larger than the planet Mercury. The photograph you see here is fuzzy, and that's not because it's a low-resolution photo, it's because that's how Titan actually looks. Titan has an atmosphere. Now, the atmosphere is opaque, which means we can't see through it here from Earth, but what we can do is observe how sunlight hits the atmosphere and reflects off of it and interacts with it. And from that, we even before we arrived there with the spacecraft, we were able to measure the chemical composition of the atmosphere. And that got interesting because it turns out Titan has a lot of methane in its atmosphere. And that's interesting because sunlight, when it hits the methane, will actually break methane down into ethane and some other chemicals. And you can calculate that all the methane in Titan's atmosphere will be gone after just 10 million years. Now, 10 million years sounds like a long time, and it is, but compared to 4.5 billion years, it's no time at all. Realize that a billion, with a B, is 1,000 million. So 4.5 billion is actually 4,500 million years old. That's how old Titan is supposed to be, because that's how old the solar system is supposed to be. But that methane would be gone after just 10 million years. So it's supposed to be 4,500 million years, but after just 10 million years, all that methane would be gone. Yet the methane is still there. There's still measurable methane. So, okay, secular scientists said that's not a problem. Apparently, there must be some sort of source below the atmosphere that we can't see through at this point that's replenishing the methane in the atmosphere. And in addition, since we know, quote unquote, Titan is 4.5 billion years old, that means there's 4.5 billion years worth of ethane and other byproducts built up on Titan's surface. So you understand the logic here. If Titan is actually billions of years old, you need two things. You need large reservoir of methane to keep resupplying the atmosphere, and you need 4.5 billion years of ethane and other things produced by all the methane that's been breaking down for these billions of years. Now, Titan is a very cold place, so methane and ethane on the surface would actually be liquid. So people calculated and said, well, if this is actually billions of years old, and they weren't questioning this in the calculations, by the way, these are secular scientists, then we expect there to be a global ocean of methane and ethane on Titan's surface. Well, when we actually got to Titan a few years ago and sent a lander down to penetrate the atmosphere, we didn't find a global ocean. This is a photograph from the surface. It's dry. There's a few lakes up in the polar region, but no global ocean that the billions of years would require. Titan doesn't look billions of years old. Titan looks much younger than that. Moving outwards in the solar system, we have the planet Uranus. And again, there's more we could say about this and its neighbor Neptune if we had time, but I'll limit my comments tonight to just the fact that, according to the secular model, those two planets don't exist either. As this article in Astronomy Magazine pointed out, astronomers who model the formation of the solar system have kept a dirty little secret from you. Uranus and Neptune don't exist. Or at least computer simulations have never explained how planets as big as the two gas giants could form so far from the sun. Bodies orbited so slowly in the outer parts of the sun's protoplanetary disk that the slow process of gravitational accretion, i.e. the planetesimals sticking together, would need more time than the age of the solar system to build planets out there. It actually turns out that if you're going to build these planets from the planetesimals and then they gather gas and so on, you need 10 billion years to produce planets out there. Now, the solar system, even from a secular perspective, is supposed to be less than half of that, only 4.5 billion years. So these two planets shouldn't be there. You would think that would be a problem if you're going to claim you have a good secular model, right? It's clear that our level of sophistication of studying planet formation is relatively primitive. So far, it's been very difficult for anybody to come up with a scenario that actually produces Uranus and Neptune. Now, who heard about these problems in Cosmos or Discover Magazine or any other secular science media? No, that's not the perspective that's presented, right? It's, oh yeah, we have it all figured out, 4.5 billion years, this happened, this happened, this happened. They don't tell you about all these other problems. And again, I'm quoting the scientists themselves here. I'm quoting their own journals. But this isn't what the public is being told about. And I like this quote here because it says it's difficult to come up with a scenario. Unfortunately, science, in the age of secular naturalism, has really veered off from what is verifiable in a scientific sense to just coming up with scenarios and claiming that it must have happened that way. We're getting away from model building and more toward storytelling to paper over some of these gaps in the models. As an example, to explain away some of these problems, this article says, a wandering Jupiter accounts for our unusual solar system. In other words, Jupiter didn't form where we see it today. It formed somewhere else. It wandered around the solar system for a while, wreaking havoc as it went, by the way, and then wound up where it is today. Where's the evidence for that? Well, the evidence is that the planet is where we see it today. Is that a good model? What evidence do you have that would confirm or falsify that model? It's not really a scientific model then. It's really just storytelling, right? Because there's no way to confirm or falsify it. Other people are proposing that there's been giant planets ejected from the solar system. In order to solve certain problems in the model, they proposed all these other planets were there that did various things and then interacted with each other, and then they gravitationally flung some of them out, and they're all gone now. And only the ones we see today are left behind. Is that a scientific model? I mean, the evidence for this is what? That the planets aren't visible anymore. No, that's just storytelling. Our solar system may have once harbored super Earths. Earth belongs to a second generation of planets. To explain some problems now, some people are proposing that there was a whole first generation of planets that formed, interacted with each other, did various things, and then got destroyed, and they're all gone now, and all the ones we see today are the second generation. How do you confirm or falsify that story? Well, that's because it is just a story, not a model. And I like this one. Did Jupiter and Saturn play pinball with Uranus? Uranus can't have formed where it is in the solar system today. Therefore, thinking like a secular scientist, it must have formed somewhere else because we know it formed all by itself, right? Well, one place it could have formed, supposedly, is out where Jupiter and Saturn are. Of course, it's not there today. Well, see, what happened was Jupiter and Saturn kind of played ping pong with it for a while. It went toward Jupiter, and then Jupiter flung it over to Saturn. Saturn flung it back, and it did that a couple of times until Saturn missed the catch, and then Uranus kept out, traveling further into the outer solar system where it is today. And there's this helpful scientific simulation over here to show you what that was like. But is this a model, or is this just storytelling? I think the answer here is clear. I mean, there's an infinite number of stories you can come up with, right? All of which would end in a set of planets that we see today. Those aren't models, they're stories. Bottom line of all this, thus far we have seen that we know very little about the development of our solar system. That's from one of my astrophysics textbooks. To sum up, I think that all suggested accounts of the origin of the solar system are subject to serious objections. The conclusion in the present state of the subject would be that the system cannot exist. Well, that's a nice summary, but it does exist. My overall point is, this part of the model doesn't work very well. So let's go back to an earlier part. What about the formation of stars and galaxies? Well, if we're going to talk about stars, let's first of all talk about what stars are. A star is basically a big hot ball of gas out in space. And they come in different sizes and different temperatures and different masses and different colors to a limited extent there. But they're all basically big hot balls of gas. Now, if you want to have a secular model of origins, you need to explain where stars came from, because the basic building block of the universe is stars. There's a few planets here and there, but in terms of mass, they're insignificant. Basically, reality is made up of stars, because stars together make galaxies, and galaxies are what we see out there. Now, what we're told is secular scientists have this good model for explaining star formation. Supposedly, there was these clouds of gas that collapsed under the force of gravity. And we do indeed see many clouds of gas out in space. I have some photographs here. I'm showing you one here, for example. And if you picture a gas cloud, all the molecules of gas in the cloud, they're all interacting with each other gravitationally. Each molecule is pulling very slightly on all the rest of them. Now, there's not much of a force for any given molecule because they're just molecules. But if you have a big enough cloud, they're all pulling on each other. That means they're all going to move toward their center of mass. So gravity will make this cloud contract. And as it contracts, it compresses. And if you remember your high school chemistry, what happens when you compress a gas? It gets hotter. So gravity compresses, it gets hotter and hotter and hotter. Eventually, you reach a point where nuclear fusion ignites deep inside this thing, and now you have a star. So this is how we're told stars form. Cloud of gas, gravity, compresses it, makes stars. No problem, right? Well, actually, there is a problem. See, gravity is not the only thing at play inside these clouds. There's also gas pressure. And to illustrate this, I have a very expensive piece of astrophysics test equipment here, a can of compressed air. Now, compressed air, by definition, the air is compressed in here, or gas, I should say. It's not actually air. Now, what happens when I squeeze the trigger and open a passageway in between this high-pressure system and a lower-pressure environment? Gas comes out, right? Now, nobody's scared when I do this, I notice. Nobody's worried that instead of gas coming out, it'll actually suck all the gas in the air, all the gas in the room into the can, leaving us in a vacuum. We'd all asphyxiate and die. No one's worried about that, obviously, right? That's a stupid thing to say. Why is that? Because the gas always flows from higher pressure to lower pressure. right? The only reason I can keep a system of high-pressure gas is because it's in an enclosed container. But there's no containers out in space, right? So what is it that will keep these clouds together? Well, gravity is, as I said, at play in these clouds, but it turns out gravity is much weaker than gas pressure. So the clouds we see would actually dissipate under gas pressure, because that it will overcome the force of gravity. Here's another way to look at this. Imagine you have this cloud of gas here, and then here's space. So here's the boundary between the two. Now, in a gas cloud, all the molecules are moving in different directions, right? And they're all bouncing off of each other. I mean, same thing's happening in this room right now. All the little molecules are rebounding off of each other. Now, the ones in here are just hitting each other and staying in the cloud, and that's fine. Imagine the ones on the very outer layer, though. On average, half of them will have a motion going inward in some direction or another. Some will be moving directly in, some will move more this way, but give or take half of them will be moving inward. Those will collide with others in the next layer in and stay in the cloud. The other half, though, will have a motion going outwards, some directly out, some just this way, but regardless, outwards in one form or another. They're not going to have anything to collide with, will they? They're going to keep going. So the cloud will lose part of that outer layer of gas molecules, and then this process continues. So it loses layer after layer after layer after layer, and you keep peeling the onion until eventually there's no onion left, right? Same thing happens here. A gas cloud in space will dissipate, not contract. Now you may be wondering, well, wait a minute. A few slides ago I told you a star is just a hot ball of gas out in space. Why don't stars dissipate? Because a star is already dense enough, which makes gravity strong enough to hold it together. Gravity is stronger over shorter distances. Key point. So once you have a star can be stable. When it's still a gas cloud, though, gravity is weaker, and so gas pressure is going to drive that cloud apart. Do secular scientists know about this problem? Well, yes, they do, and they have several proposed solutions. They have compression, cooling, and collision, so let's talk about each of these briefly. Compression comes from a supernova. Well, a supernova is a big explosion in space, a very violent explosion. This one here is a supernova. Next to a parent galaxy, you see how bright it is compared to the whole galaxy. We've seen several supernovae go off, and some of them left remnants behind. The Crab Nebula, for example, this is what happens after a supernova. There have been actually a few in more recent times, and we've actually been able to watch with telescopes. It's been very informative about some of the processes at play here. But the idea is this, that you have this gas cloud, and a supernova goes off next to it. The shock front from the supernova compresses the cloud enough to make it dense enough that gravity can then take over, overcome gas pressure, and sort of kickstart the star formation. So compression is the first of these proposed mechanisms for making stars. The second one is cooling. What happens if you have a pot of water that's just barely starting to boil on the stove, and you dump in a box of rice? The water does what? Stops boiling, right? Why is that? Well, because the rice absorbed some of that heat that was bringing it to a boil. Same thing here. If you blow a bunch of particles into a gas cloud, that will actually cool it down. And if you cool down a cloud, it will reduce gas pressure, which means gravity will make it shrink. And if that happens to a large enough extent, gravity can then again take over, compression continues, and you get stars. So we had compression, we had cooling, and then the third proposed explanation is collisions. I'm showing you a photograph of what appears to be two galaxies colliding. And galaxies are collections of stars and dust clouds in between the stars. So when you crunch together dust clouds, what are they going to do? They're going to compress. And that can overcome gas pressure enough to make some stars. And indeed, we see what appears to be some young stars in the collision front in places like this. But there's a problem with all three of these explanations that maybe you've noticed. I told you that a supernova is a giant explosion out in space. I didn't tell you what is exploding. The answer is an old star. Not all stars will go supernova, but those that do, under certain circumstances, again, they all used to be stars. The grains and the particles necessary for cooling, to blow into a cloud to cool it off, where did they come from? Well, it turns out the Big Bang can't make any. Big Bang can only make gas. If you want grains and particles, that had to be formed inside the cores of stars as a byproduct of their nuclear fusion. And of course, if you want galaxies to collide, well, they're just big collections of stars, too. So does anybody see the problem here? In all three of these explanations, in order to make stars, you first need stars. So what kind of problem is this? It's the classic one, right? Chicken and the egg. You need eggs to make chickens, you need chickens to make eggs. Same thing here. All the mechanisms to overcome the problems of star formation all require stars to already exist. Don't they recognize this? Well, yes, they do. The process by which an interstellar cloud is concentrated until it's held together gravitationally to become a protostar is not known. Literally hundreds of ideas on how stars are formed have been advanced in past decades, but we are still far from any real solution. The origin of stars represents one of the most fundamental unsolved problems in contemporary astrophysics. Again, who heard Neil deGrasse Tyson talk about this in Cosmos? No hands go up. The formation of stars is one of the most fundamental problems in astrophysics. No current model can reproduce all of the observations. Well, that last part's not true. The biblical model works just fine. Great is our Lord and of great power, his understanding is infinite. So what you aren't being told about star formation is that gravity is being invoked to pull together gas clouds, but that's a weak effect compared to the gas pressure, which will force them to disperse instead. All the proposed answers for that problem requires old stars in order to make new ones. And of course, if you don't have stars, that means you don't get galaxies in your model either, because galaxies are just collections of stars, aren't they? Which is why a completely satisfactory theory of gravity formation remains to be formulated. The formation of galaxies on larger scale structure remains TMI-UPIMA, the most important unsolved problem in modern astrophysics. The universe we see when we look out to its furthest horizons contains 100 billion galaxies. Each of these galaxies contains another 100 billion stars. That's 10 to the 22 stars all told. A 1 with 22 zeros after it. That's a large number. The silent embarrassment of modern astrophysics is that we do not know how even a single one of these stars managed to form. There's no lack of ideas, of course, we just can't substantiate them. So moving back to our secular timeline, we see that the star formation part doesn't work very well, which means the galaxy formation doesn't work either, which means our Milky Way galaxy is unexplained. What about the beginning, at the whole timeline, though, the universe itself? What about that part? Well, what we're told is this. In the beginning, there was this big bang, which formed the gas from which the stars and the galaxies and everything else came. Now, we just saw the stars and the galaxies part doesn't work very well, but let's focus on that actual beginning. On websites like NASA's, you'll see this diagram. This is a fairly popular one. This is a diagram where this is a dead battery and a laser pointer is what that is. There we go. So this is the beginning of history, and this is where we are today. So time goes left to right. So there was this quantum fluctuation, which was the Big Bang, an immediate period of inflation, and you see it went from a dot to a very much larger size here. Today it's larger than it was back then, but you see how there's mostly expansion in the beginning. We'll talk about that. I shouldn't say most expansion, but a rapid period of expansion in the beginning. We'll talk about that. And we are told that there's lots of evidence for this model. What evidence would that be? Well, first of all, faraway objects appear to be redshifted. Redshifting is a certain property of the light that I won't go into today. You can look it up if you're curious, but it's interpreted to mean that everything is moving away from us. So if you picture that we're in one of these galaxies and that as time goes on, all the galaxies are moving apart, well, mentally run that movie backwards, it means that everything used to be closer together, and then meant to all run the movie even further back, and everything is in the same place, which is thought to be the Big Bang. So redshifts, in their interpretation of everything moving apart, again, mentally run the movie backwards, means that further back in history it was all like this. If everything came from the same point in space, then that would be the idea behind the Big Bang. You will also be told that the abundance of light elements, the amount of hydrogen and helium and lithium, especially lithium, in the universe, corresponds to this model and is evidence for it. And you will also be told that we have the cosmic microwave background, which is this pattern of radiation out in space that is left over from the Big Bang. And I don't have time tonight to really dig into the details of each of those, and again, you can easily go look all that up on your own if you'd like to. I just want to mention it tonight, A, to point out that yes, I'm aware of what this evidence is, and B, the fact that this evidence doesn't necessarily support the Big Bang. In fact, some of it, as we're digging further into it, appears to be evidence against the original Big Bang model. For example, the cosmic microwave background, as we're getting better looks at it, is showing a pattern that does not match this random Big Bang model that has become known as the axis of evil. The apparent alignment in the CMB, the cosmic microwave background, in one particular direction, is called evil because it undermines our ideas about the standard cosmological model. In other words, we're seeing patterns of temperature differences and regularities within that background radiation that do not match the Big Bang model. And we could talk more about that if we had more time. I'd like to spend a few minutes, though, talking about this overall idea of the Big Bang happening at all. In the beginning, according to this idea, there was nothing. And then it exploded. What exploded? Nothing exploded. How can nothing explode? Well, nothing did explode. Nothing can explode and does, apparently, because that's why we're here. That's why there's everything rather than nothing. See how easy that is? There are books that explain, supposedly, how we get a universe from nothing. But this doesn't really make sense if you think about it. I'll return to this book here in a moment. The Big Bang requires us to go from nothing, literally nothing, to everything. But nothing can create nothing, right? Nothing can do nothing. From nothing, nothing comes. R.C. Sproul once said, if there ever once was truly nothing, there could never be anything. Which, if you think about it, makes sense. And Dr. Phil Fernandez, who will be speaking here in July, and I recommend you all come to see his talk, he once said, you can't tell me nothing made everything, because I know too much about nothing. Sometimes people will say, well, if you wait long enough, even that which is extremely improbable will eventually occur. Well, that doesn't help you, actually, because the Big Bang supposedly made four things: matter, energy, space, and time. There was no time before the Big Bang. And this comes out of relativity, actually, because space and time are interwoven in general relativity. And if the Big Bang made space, it also made time. Therefore, there was no time before the Big Bang happened. Therefore, you can't wait long enough for anything to happen because there's no time within which to wait. Nor is there a place you could wait anyway. Nor does this even help you, because nothing creating everything isn't just improbable, it's impossible. And you can wait as long as you like. That which is impossible will never occur by definition. There's also the question of who did this or what did this. How did this all happen? Well, if the Big Bang popped into existence out of absolutely nothing, then the Big Bang created itself. The universe created itself. But something can't create itself, because in order to create something, that which created must first exist, right? Self-creation would mean that the thing exists before it existed, which doesn't make sense. Now, there are scientists today who will tell you, no problem, we have an explanation for all this. For example, Stephen Hawking explains that because there is a law such as gravity, the universe can and will create itself from nothing. Spontaneous creation is the reason there is something rather than nothing, why the universe exists and why we exist. Notice, by the way, move on. He explained further that the laws of gravity and quantum theory allow universes to appear spontaneously from nothing. Notice this word, universes, plural. We'll come back to that. My point for now is, what is he crediting for the creation of the universe? The laws of physics, right? The laws of physics can create the universe. They're responsible. Well, wait a minute. What does a law of physics look like? What does it feel like when you hold one in your hand? That's a stupid question, right? It's not a thing. What is a law of physics? Well, it is, if you think about it, a law of physics is just a pattern. It's a pattern of behavior that we have noticed in the universe around us. If I open my fingers, a laser pointer will fall to the floor. And I can do that over and over again. It'll keep doing that. Eventually, I can try different heights. I can try different masses. Eventually, I can notice that this pattern of behavior is regular and has different aspects to it. And if I figure it out enough, I can maybe codify that in a mathematical formula and call it the law of gravitation. Now, the law of gravitation is not a thing, right? It's just a pattern of behavior that I've noticed and that I capture into an idea. So to say that the laws of physics we're somehow responsible for the universe creating itself is silly, because the laws of physics aren't things. They can't create anything. And as this secular author points out, a more fundamental problem is that this scenario does not really explain the origin of the universe anyway. A quantum fluctuation of the vacuum, remember the Big Bang is supposedly a quantum fluctuation, assumes that there was a vacuum of some pre-existing space. And we now know that vacuum is very different from nothing. Vacuum, or empty space, according to general relativity, has energy and tension. It can bend and warp, so it is unquestionably something. From the point of view of general relativity, empty space is unambiguously something. According to general relativity, space is not a passive background, but instead a flexible medium that can bend, twist, and flex. A proposal that the universe was created from empty space seems no more fundamental than a proposal that the universe was spawned by a piece of rubber. It might be true, but one would still want to ask where the piece of rubber came from. You will see this in many of these books. They'll tell you that the universe popped into existence out of nothing, but when you dig deeper, they don't really mean nothing. Now they're saying empty space and a pre-existing vacuum. Well, as these scientists are pointing out, empty space, according to relativity, is not nothing, it is something. So where did the something come from? And why did it suddenly decide to create a universe for no reason? No problem, say some secular scientists. We have an explanation for this too. Back to Lawrence Krauss's book, he says quantum gravity explains how that vacuum, that initial vacuum, got there. He says a quantum theory of gravity allows for the creation, although perhaps momentarily, of space itself, where none existed before. So quantum gravity did it. Problem: modern physics doesn't actually have a theory of quantum gravity. Neither does Dr. Krauss, as he himself admits. I also don't have a quantum theory of gravity, so I can't tell you for certain how space comes into existence. Isn't that nice? This whole idea also has other problems. Number one, it runs afoul of some very basic physics, like the conservation of mass and energy. If any of you have taken a physics class, you're familiar with this idea that the overall amount of matter and energy in the universe is constant. Now, matter and energy are now understood to be different versions of the same thing. You may have heard E equals mc squared, right? The famous equation. E means energy, m means mass, and c is the speed of light, which is a large number. So remember your algebra, that means a large number, that one, times m equals E. So that means a little bit of m equals a whole lot of E. In other words, a lot of energy is contained in a little amount of stuff. Now we can convert those two things back and forth. We can liberate the energy from the stuff, or we can convert the energy to, we can convert the mass to energy. And I said that wrong the first time around, didn't I? Sorry if I confused anybody. We can convert energy to matter, and we can convert matter to energy, but we can't create or destroy the total amount in the universe of either of those. For example, how do we convert matter to energy? Well, the most efficient way we know how to do that is a nuclear explosion. A little bit of stuff turns into a lot of energy, right? We can go the other direction. Particle accelerators, we take a lot of energy and make a little bit of stuff. They get particles zipping around at close to the speed of light, they smash together. More particles came out of the collision than went in. We're translating their kinetic energy, the energy of their motion, into physical matter. But we're not creating the mass energy in a net basis for the universe. Does anybody understand the point I'm making here? You can convert this to that and convert that to this, but the total amount of both of them added up is always constant in the universe. And we see the results of this all around us. Why do we have to eat food constantly, despite how difficult that might sometimes be? Because your body needs energy, and you can't make energy from nothing. So you have to get it from the stored chemical energy in the food you eat. Why do we have to pay the bill to the electric company every month? Well, because your house can't get energy from nothing. It has to get it from somewhere else, in this case, the power company. The power company also can't make it from nothing. It gets it by burning coal, liberating chemical energy, or it gets them from hydroelectric, which means it's converting gravitational energy, and so on. All of that ultimately, in one form or another, comes from the sun, which itself can't produce energy from nothing. It's burning its mass as fuel. So I'm trying to communicate how fundamental this idea is even to our daily lives. It's also all throughout physics and engineering. The fact that we're listening to this presentation and watching this tonight verifies that this principle is true, because the principles of circuit design are based on the conservation of mass energy. And if you ever take a physics class, most of the problems you solve as homework will basically assume that this principle is true, apply it to the specific problem you have, and then work out the implications and solve it. And if you were to ever suggest that this principle is not true in class, I mean, automatic fail. Goodbye. But the Big Bang violates this on the largest possible scale. It says the whole universe popped into existence out of nothing. It violates the most fundamental principle in physics on the largest possible scale. Now, tell this to a secular scientist and you'll get a patronizing smile. Oh, you poor creationist, you don't understand the beauty of the Big Bang model. You see, it's true that nothing made everything, and that would seem to be a violation of the conservation of mass energy. But that's not a problem, because although nothing made everything, everything is really nothing. So on a net basis, the Big Bang didn't actually make anything, because everything is really nothing. What do they mean by that? Well, you can model the universe in such a way that you add up all the energy and mass, and you get a number. We'll call it X. And you model how it's distributed in the cosmos, and you see what gravitational energy results from that, and you can model that in such a way that that's negative. It turns out that those two numbers are pretty close to being the same. So the idea is this: if mass and energy is a positive number, and gravitational potential energy is a negative number, positive plus negative equals what? 0. So the popular idea today, bandied about in cosmological circles, is that the universe on a net basis is nothing. Therefore, the Big Bang didn't really create anything. Therefore, this fundamental principle in physics isn't violated. As Stephen Hawking explained, the laws of physics demand the existence of something called negative energy. To get your head around this weird but crucial concept, let me draw a simple analogy. Imagine a man wants to build a hill on a flat piece of land. The hill will represent the universe. To make this hill, he digs a hole in the ground and uses that soil to build his hill. But of course, he's not just making a hill, he's also making a hole. In effect, a negative version of the hill. The stuff that was in the hole has now become the hill, so it all perfectly balances out. This is the principle behind what happened right at the beginning of the universe. When the Big Bang produced a vast amount of positive energy, it simultaneously produced the same amount of negative energy. In this way, the positive and negative add up to 0, always. It's another law of nature. So what does that mean? It means that if the universe adds up to nothing, then you don't need a God to create it. The universe is the ultimate free lunch. Who can spot the flaw in the analogy? Flat ground, hole equals hill. Add them together, you get nothing. There's a problem though, right? How do you get the hole? You need someone with a shovel, right? You need an external agent to the system who expends calories, energy, in order to make this divergence, right? Don't you? Holes spontaneously don't form themselves. A more concrete example I like to use of this one, I once worked on a circuit design where one part of the circuit had to power another part of the circuit, and it did that by, we'll call it 2 wires. One produced plus 40 volts and one produced minus 40 volts. And if negative voltage sounds weird, don't worry, you can do that in electronics. Now, I could argue that on a net basis, this part of the circuit produced 0 volts, right? Plus 40 minus 40 equals 0. That's the same logic Dr. Hawking is using, right? But funnily enough, when I unplugged the thing from the wall, those voltages went away. The thing stopped working. Why is that? Because the universe doesn't spontaneously diverge into offsetting positive and negative energies unless A, there's some kind of mechanism to force it to do that, in this case an intelligently designed mechanism, and B, an external source of energy to force it to do that. Neither of which are available on the secular Big Bang model. Getting back to the ultimate free lunch comment, I was once giving this lecture and a student pointed out, the problem with this is that someone had to make the lunch. Big Bang has some other problems too. I won't spend time on these, other than to point out that it made several major predictions that caused problems until the invention of an idea called inflation. I pointed out earlier in the Big Bang diagram that very rapid expansion is now a fundamental part of the Big Bang model. Basically, the universe popped into existence out of nothing. We already talked about that part. and then rapidly expanded, and then the expansion got a lot slower from that point on. Now, this does actually solve some of the major problems that I just mentioned here, these three. The problem is that this is really just a just-so story because this inflation process actually has no basis in physics. As this author pointed out, what drove inflation? Nobody knows. Physicists have suggested different models to describe the inflating universe, but all the solutions are mathematical conveniences with no particular physical basis. All the theories of inflation amount to proof that we don't have one good theory yet, says this astrophysicist. Inflation's theoretical underpinnings may be rather tentative. The inflaton, this is the particle that supposedly did the whole thing, is a hypothetical field whose existence has yet to be demonstrated. Its potential energy curve is posited by researchers, not revealed by observation, and so on. Basically, the Big Bang model needs inflation to cover up some otherwise fatal problems with it. Therefore, inflation is believed by most cosmologists today to be true, but it's based on a particle, the inflaton, which has never been seen. Not only has it never been seen, by the way, there's also no room for it in the standard particle model of physics. So inflation comes from a hypothetical process based on a hypothetical particle that's not only never been observed, there's no room for it within physics, no basis for it within physics, but it must be true because otherwise the Big Bang model will be falsified. You see the logic there? I'm going to skip a little bit of this here. Other than to point out that inflation is having increased dissatisfaction with it among some circles. Moving on, we see that secular origins models also have a problem called fine-tuning. In my Stars and Galaxies presentation, I point out that not only is the Earth finely tuned, which there's actually been books and movies made on that, some from secular authors, by the way, about how amazingly fine-tuned the Earth is to support us. You can make the same argument about the Sun. The Sun is actually unique among solar-type stars in its design characteristics to support us here. But since we're talking about the universe tonight, we can also point out that the universe itself has characteristics that even secular authors had described as being finely tuned. Skip a little bit of this here. This author said a change of as little as 0.5% in the strength of the strong nuclear force, or just 4% in the electric force, would destroy either nearly all carbon or all oxygen in every star, and hence the possibility of life as we know it. Change those rules, those numbers within physics, just a tiny bit, and the conditions for our existence disappear. Most of the fundamental constants appearing in our theories appear fine-tuned. If they were altered by only modest amounts, the universe would be qualitatively different and in many cases unsuitable for the development of life. For example, if protons were 0.2% heavier, they would decay into neutrons, which would destabilize atoms, and that would be a very bad thing, by the way. Who said this? Stephen Hawking, who, if you didn't know, is an ardent atheist. The laws of physics themselves appear to be finely tuned. The Big Bang model also has specific fine-tuned problems of its own, even beyond the laws of physics. Someone once calculated that in order for the Big Bang to have produced the universe we see today, the odds of that, or had to be finely tuned rather, to within 10 to the 60th power. So write a 1 with 60 zeros after it, 1 out of that number is the precision we're talking about. Here's a more concrete illustration of that. There's roughly 10 to the 80th power atoms in the universe. If the Big Bang had to be finely tuned to within 10 to the 60th power, you can divide that through to say that it could only have varied by 10 to the 20 atoms either way. And it turns out that if the Big Bang had had 10 to the 20 atoms more, then you would have had runaway gravitational collapse, and we wouldn't be here, according to the Big Bang model. If it had created 10 to the 20th atoms less, then galaxies could never have formed because expansion would have pushed everything apart too quickly, and again, we wouldn't be here. So the Big Bang had to create the universe to a precision of 10 to the 20th atoms. How much matter is that? It's about the same amount of stuff contained in a grain of sand. So think about that. Think about how big the universe is. A random Big Bang had to create everything we see down to the precision of a single grain of sand. If it created 1 grain of sand's worth of stuff too much, runaway gravitational collapse. If it had created 1 grain of sand too least, less than what it did, then runaway expansion, galaxies would never have formed. Does that sound reasonable, that a random event would have done that? Now, in fairness, I should point out this is one of the problems inflation was supposed to solve. But it turns out that subsequent to that, people have realized the problem is even worse. Now it's up to 10 to the 123rd power. That's a 1 with 123 zeros after it. That's this number. 1 out of that number is the precision that the Big Bang now needs to have had. Again, applying our illustration here, if there's 10 to the 80th atoms in the universe, finely tuned to the 10 to the 123rd, that means the precision is 10 to the minus 43 of an atom. That's this fraction of an atom. That amount of stuff, if you can slice up an atom into that many different pieces, one of those slices is how finely tuned the Big Bang had to be. This random event that didn't have a creator involved. This avowedly secular scientist said this is a cataclysm for physicists, and the only way that we know how to make sense of it is through the reviled and despised anthropic principle, which is the idea that the universe had to be created for man somehow. Is there an explanation for this? Well, yes, there is. They say, yes, it appears extremely unlikely that the Big Bang made our universe, but that's not a problem because this isn't the only universe. You see, there's actually an infinite number of universes out there. And with an infinite number of universes, even the most unlikely combination of characteristics will be out there somewhere. We just happen to be in one of those extremely unlikely ones. This idea is now called the multiverse, for multiple universes. And you might be scratching your head saying, well, how can there be more than one universe? By definition, universe means everything there is. Well, they redefine the word. Universe now means that which we could ever possibly perceive, even with the best possible technology and so on. If reality is much bigger than that which we could ever perceive, all those other non-observable places, they're now calling other universes. And it turns out that the Big Bang actually will produce an infinite number of universes through a process of eternal inflation. The original idea of inflation said inflation happened, boom, there's the universe, and that was it. Subsequent work has revealed inflation, once it starts, can never stop. It will keep producing an infinite number of bubble universes through eternity. And this may sound goofy, but a lot of people actually are happy about this because that makes the infinite number of universes, which explains the fine-tuning problem, right? But is it really a good explanation? Think about the implications of this. If there's an infinite number of universes out there, let me back up a minute. There's an infinite number of universes with a solar system just like ours, with a planet called Earth in the third spot from the sun, where we are all in the same room having the same discussion. Right? If there's an infinite number, then this same room is out there an infinite number of times. Even secular authors talk about this. Is there another copy of you reading this article, deciding to put it aside while finishing the sentence, although you're reading on? A person living on a planet called Earth with misty mountains, fertile fields, and sprawling cities in a solar system. The life of this person has been identical to yours in every respect, until now, that is, when your decision to read on signals that your two lives are diverging. You probably find this idea strange and implausible, but looks like we'll just have to live with it because the simplest and most popular cosmological model today predicts that this person actually exists. If space is infinite and the distribution of matter is sufficiently uniform, then even the most unlikely events must take place somewhere. There are infinitely many other inhabited planets, including not just one, but infinitely many, with people with the same appearance, name, and memories as you. There's an infinite number of universes out there where we are all having the same exact discussion, same as this one, except that you, sir, had something different for breakfast this morning. There's an infinite number where the South won the Civil War. There's an infinite number where there never was a Civil War because the 13 colonies lost the revolution against King George III. On and on it goes. Every possible combination of circumstances is out there an infinite number of times somewhere. And this is big business now, by the way. These are just some of the books I could fit on the slide. All the multiverse books. If you want to make some extra money, go write a book about all the universes no one can ever see. Because who can prove you wrong, right? Now, in our last part of the talk here tonight, just for a couple minutes, let's take this multiverse idea to its logical conclusion and see where we wind up. I'm going to argue that not only is the Big Bang not good science, it's actually anti-science. Because when you take it to its logical conclusion, it denies the fundamental things that must be true if science is possible. Number one, it violates physics. We talked about that already. Any scientific model that violates the most fundamental laws of physics is a non-starter out of the gate. But worse than that, if you think about it, it invalidates physics itself. What do I mean? If the Big Bang created time, and there was no time before the Big Bang, then the Big Bang could not have had a cause, right? Because a cause has to come before its effect. So the Big Bang, there was no reason for it, it just happened. As this cosmologist said, the universe is just one of those things that happens from time to time. Our universe may have resulted from a random quantum fluctuation, and this raises the remarkable possibility that the birth of our universe may have had no explicit cause. Maybe there was no ultimate cause for the universe. It just happened. Is that a scientific statement? It just happened? Is it a denial of the scientific method itself, if you think about it? The famous story about Isaac Newton sitting under a tree and seeing an apple fall. And he said, why did I do that? And then he started all of his thinking, which ultimately resulted in his law of gravitation. That happened because he said, why did it do that? That assumes that there's a reason it did it, right? If he had just said, it just happened. Random chance universe, after all. Every scientific discovery is based on the assumption that things happen for a reason. The Big Bang violates that. In fact, if the Big Bang was founded in a random event, is it consistent to expect the universe to operate according to strict laws of physics afterward? Or is that inconsistent instead? I think the answer there is clear. But of course, in order for science to be possible, it must operate consistently. Now, Christians can assert that the universe operates consistently because the Bible says so. An atheist, however, cannot say that. Another reason, multiverse is ultimately self-contradictory. Think about all those other universes that we can never see. If they're unobservable, by definition, that makes them outside the natural world, that which we can observe. And what word did we apply to things outside of the natural world? Supernatural. Even some secular scientists are unhappy with it because of this reason. These multiverse theories all share the same fundamental defect. They can be neither confirmed nor falsified. Hence, they don't deserve to be called scientific. Multiverse theories aren't theories. They're science fictions, works of the imagination. Number 4, multiverse ultimately leads you into absurdity. And I'm running out of time here. The Bible says, by their fruits you shall know them. If the Big Bang and the multiverse idea were good science, then they would produce good fruit, good results. If they weren't, though, they would produce absurd results, maybe just science fiction. Sean Carroll, prominent cosmologist, says, our universe may be the offspring of some other universe. Baby universes fluctuate into existence in both directions of time, eventually giving birth to babies of their own, etc. Each of them, in order to make his model work, here's the key point. Each of them would experience an arrow of time, but half would have an arrow that's reversed with respect to that and the others. In other words, he's got baby universes popping into existence all over the place, but in half of them, time has to flow backwards. Is that science or science fiction? Another author said, if we go exploring other planets, we have to be careful, and he wasn't talking about the multiverse specifically, but the same sort of reasoning. Dinosaurs on this planet evolved and then got killed off supposedly by an asteroid. If we go to other planets, maybe their dinosaurs didn't get killed off by the asteroid, though, so we better be careful, because if we run into advanced versions of dinosaurs, we'd be better off not meeting those. Because there's nothing worse than running into a dinosaur that has better weapons than you do. But if you're worried about running into dinosaurs on other planets, is this science? Or is it just science fiction? That's a scientific simulation there. Sorry, I can't resist. Other people are trying to explain away fine-tuning with this, that our universe was created by life of superior intelligence in another universe. That's why everything looks designed, because there was a designer, his aliens. But if you're invoking aliens, are you doing science or just science fiction? There they are. Other scientists are saying, well, maybe we're living in a computer simulation. It's a perfectly acceptable supposition that the world we know it is a vast computer program run by machines in a different universe. If you accept the multiverse idea, it's inevitable that there's computer-based universes out there, right? Infinite universes. Some of them are going to have aliens with such super-duper technology that they can simulate universes. Chances are we do live in a computer simulation of universe. Science or science fiction? I think the answer here is obvious, right? Because we think we see a cosmos around us, but it's not actually real. It's just part of a computer simulation being run by aliens. Now, you may think that this sounds pretty silly. But don't laugh, because this is a serious matter.
This is a serious matter.
See? They are actually studying to see if the universe is actually a numerical simulation. This study, by the way, is partially funded by the Department of Energy. These are your tax dollars at work to see if we live in a computer simulation. But wait, if there's infinite universes, then not only can there be aliens with technology to simulate universes, there can be aliens with technology to simulate universes that have aliens that can simulate universes. So maybe we live in a simulation of a simulation. As this author said, there could even be multiple levels of simulation. The computer our universe runs on could itself be a simulation on another computer. So not only are we not living in a real universe, it's not only a simulation, that itself is part of a simulation as well. And why stop there? Maybe that's also part of a simulation. Maybe that's not real, because that's just running on a computer that's part of a simulation, which is itself running on a simulation that's part of a computer, which is itself running a simulation that's part of a computer, and so on and so on. Now, not all cosmologists talk in these terms, but this is the logical implication of a multiverse, right? This is where you wind up, in absurdity. And if your model leads you to absurdity, I'd say that makes your model absurd. Now, why are cosmologists, who are otherwise very intelligent men and women, teaching this stuff? Well, as this scientist said, if there's only one universe, you might have to have a fine-tuner. If you don't want God, you'd better have a multiverse. The Bible says that the fool says in his heart that there is no God. Now, I'm not calling these people stupid. Again, they're very intelligent men and women. But when you deny wisdom as your fundamental starting point, wherever it is you wind up has to be folly. If you deny the truth, you're going to wind up in a lie somewhere. And that's what's going on here. I am out of time, so I'm going to stop there. I will just point out that the material, first of all, if you like this perspective on astronomy, I have a free email newsletter. It's supposed to come out once a month. In reality, it's once every few months. Lately, it's been even less than that, so you're not going to get a lot of email, is my point. Or you can go to my website, creationastronomy.com. As things happen in the news, I will present articles talking about the other side that the secular people aren't telling you about. The first part of the presentation tonight, talking about the solar system, there's actually a full, almost a 2-hour presentation on that. That's available as a DVD in the back. I gave you just the briefest highlights from that, but the full presentation goes through each planet and a lot of their moons. Each one discredits the secular origins model in a different way. I think it's a lot of fun. There's also a full presentation on the stars and galaxies portion, which you saw, again, just brief highlights from tonight. There's my website, and I thank you for the privilege of speaking to you tonight. Thanks.
All right, thank you much. So we're going to allow you to ask some questions of Spike. I'll bring the mic around. Before we get to that, we're going to take up an offering. Guys, if you come on down. Once I get down, I'll pray for the offering real quick, but you can get your offerings ready. Again, you can use the envelopes in the back, make checks out to Cedar Park. Those envelopes can also be used for credit cards if need be. So we can get one down this aisle. Maybe that could help. All right, awesome. Let me just send this up as a prayer. Father, we thank you so much for Spike and his ministry, Father, and we thank you so much for Cedar Park Church, who opens their doors and offers these kinds of educational programs. Father, we ask for wisdom. Father, we do need wisdom to understand the world, to all the teachings that are coming at us. Father, we need wisdom to understand how all this fits into your word, Father, how all this fits into the biblical worldview, Father. Give us wisdom, please, Father, and give us an opportunity to serve. Father, we lift up this offering to you and just ask that you would use it for mighty works, Father, that you would help the news of your creation, the news of your saving grace, Father, and the news of your Son, Jesus Christ, to make it to the ends of the world, Father. We lift up Cedar Park and his ministry to you. We lift up Spike to you and ask that you bless these. In Christ's name, amen. All right, we got some time for questions. I saw one hand up a little bit ago. There he is. Okay, I'm not sure how to get to you real easy. Or, there you go. I'm going to climb over you, sir. And then.
I'm assuming you know Hugh Ross. Could you speculate just a little bit on where you and he might differ and agree on your approaches to young and old Earth?
I'm having trouble hearing you. You talking about Hugh Ross?
Yeah. Could you speculate some, if you were in a debate tonight, where you and he might differ and agree?
Hugh Ross accepts the Big Bang model. He believes that that's how God did it. So he would be less critical of some of the claimed evidence for it. He would agree that the universe is finely tuned. He views that as evidence for God's creating things. If I were to talk to him, I would bring up a point that I didn't really talk about tonight. It's dangerous, I think, for anybody to base their biblical interpretation on the current scientific model that's popular today. He would dispute that he does that, by the way. He would say he found the Big Bang in Scripture first. But his whole ministry is based on the idea of the Big Bang being true. And what happens when the secular people throw the Big Bang model under the bus in favor of something else? If you look at the history of science, the current paradigm is overthrown constantly and being replaced with something new. The Big Bang has a lot of other problems that have accumulated that I didn't even have time to talk about tonight. A lot of people are growing increasingly dissatisfied with it. Inflation is necessary to solve some huge problems. There's a growing vocal criticism of inflation. Inflation itself has some fine-tuning problems of its own, by the way. Anyway, point is, if there was an alternative to the Big Bang model, there's, I think, a large part of the cosmological community that would jump to it instantly. They haven't done so at this point because they can't think of an alternative that doesn't have problems that are worse. Multiverse is getting to be a bigger and bigger trend. A number of years ago, there was someone who said, when I talked about multiverse at cosmology conferences, everybody say, it's wrong and I hate it. And today, when I talk about it at conferences, all they say is, I hate it. Multiverse is getting increasingly popular and mainstream, really, within the cosmological community. And that does away with a beginning, ultimately, because our universe, the Big Bang was just one that happened in an eternal string. It's been going on forever. That removes the need for a creator. And if you're going to base the credibility of your biblical apologetic on whatever secular scientists happen to be saying today, when they all change their minds tomorrow, you're going to be mighty lonely. And you're also going to have built a foundation that's crumbling under your feet. So, to answer your question specifically, he would agree with fine-tuning. He views that as strong evidence for a creator. He would like the idea of the Big Bang more than I do. I don't know where he stands on the multiverse thing. I haven't read his stuff in a while. I would assume he's resistant to that growing trend, though, but there's not much he can do about it. That's where the secular community is going. So, I hope that answers your question. Yes?
Hi. First of all, thank you for taking my question. Second, do you think that the current biblical model denies the possibility of modern star formation?
No. Once you have stars, they can interact and make more. I don't think it's necessarily as easy as what's often claimed, but I think there's good evidence for it in some places. For example, those galaxies that are colliding that I showed you. There's a line, a collision front, not a line, but there's a collision front where those two galaxies are interacting where there's a lot of blue stars. And blue stars have to be young by anybody's definition because they can't last very long. They burn very hot and then they're not there anymore. So whether you're looking at it biblically or from a secular perspective, both sides would agree that blue stars are much younger. They have to be much younger than the rest. So yeah, I mean, galaxies colliding can make stars. There's specific examples of existing stars interacting with gaseous clouds that are doing various things. So I don't dispute that stars can be forming today, but where did the very first generation come from is the source of the problem. Anybody else?
For the
Speak loudly, please, because I don't have a good speaker up here.
for the dark matter, would you know why it is needed for the Big Bang evolutionists?
I heard dark matter, and then I couldn't make out the rest of your question.
Why would it be needed for the Big Bang evolutionists?
Chris, could you repeat that?
Yeah, why is dark matter necessary for Big Bang cosmology?
Yeah, I didn't. Dark matter is not really a Okay, I shouldn't say that. It's necessary to solve several problems. It's not the only possible solution, but there's problems with stars orbiting within galaxies. There's problems of galaxies orbiting within galaxy clusters. None of that's really cosmological, though. The Big Bang needs dark matter. That positive and negative equals zero thing that I mentioned, dark matter and dark energy are both necessary to be part of that. Without those, you only have about 5% of the number you need. So dark matter was not conceived of initially to solve a Big Bang problem. I don't want to make it sound like I'm saying that. It was going back to Zwicky in like the 30s, I mean a long time ago, to solve some other problems where it appeared that things were orbiting in ways that they wouldn't necessarily otherwise be expected to do. But once that idea was accepted, it then was realized, oh, that would solve some other problems in the Big Bang. That's a complicated topic, and I can't really do justice to it in a couple sentences. Talk to me after if you want more details on that. Yes?
Is it correct that Fred Hoyle devised the term Big Bang as a term of derision?
Yes. Fred Hoyle, Sir Fred Hoyle, was a steady stater. He explicitly did not like the idea of the Big Bang because he didn't like the idea of the beginning because that sounded too much like Genesis. So he was one of the primary proponents of the steady state model, which said that the universe has been there forever. And that was actually the more popular cosmology up into the early 60s until the discovery of the cosmic microwave background. At that point, the steady state model can't explain that, and so that kind of did that in. But that was the primary secular cosmology of the time. And yes, Fred Hoyle first came up with the phrase Big Bang as a derisive term, but then it was subsequently embraced. Yes, sir.
Inflation in the multiverse. It leaves me wondering why inflation would create different universes. Wouldn't it be logical to state that universes created by inflation would be identical?
Not necessarily, because, well, we're getting into real speculation here too, because there's no such thing as inflation. The idea that it's eternal comes from quantum effects. If inflation goes from a dot to something yay big, I think it's a little, roughly this size, give or take, grapefruit, beach ball, whatever, instantly, pretty much. Now, in order for inflation to stop, the inflaton has to go down its curve, its energy curve, simultaneously all the way across the volume of this entire new universe. Quantum uncertainty says that it's not going to be at exactly the same energy level at every point within that volume. So even as this universe cools, the inflatons within it will fall below the point necessary to power inflation, but a few of them will still be above. And even though they're only above just for that tiny fraction of a second, inflation is such a rapid process that those tiny points instantly balloon out to form new universes. So even, like I said, once it starts, it can never stop. This one spawns more exponentially. And they won't necessarily even have the same laws of physics within them. Even if they have the same laws, they might have different values for the constants of physics. So you still might wind up with very different universes within them. And again, this is all speculative and hypothetical. I'm just telling you where their models take them. But the infinite universes don't necessarily look anything like this one. Different laws of physics, where are you going to wind up with that? You can go anywhere. Yes, sir.
The fine-tuning argument is fairly compelling, but to most people it would seem pretty abstract. I think a more convincing argument that would dissuade them from intelligent design would be this argument from size. Why is the Earth so insignificant in such a huge universe? In other words, just the argument of bigness. What would be the apologetics in that case?
The heavens declare the glory of God. The fact that the one who created this took on human form and died for us. When you really grasp the implications of that, I mean, think about how big the cosmos is. John chapter 1, Colossians chapter 1, Christ was the creator. He did this apparently as an afterthought. If you look at day 4 in Genesis, it says he made this. Oh, and he made the sun and the moon, and he made the stars also. It's like, by the way, poof, there's the rest of the cosmos. The one who made the universe as an afterthought nevertheless cares for us enough to have done what he did.
Thank you.
So that's how I look at it.
All right. Oh, one more. You're going to wait till I'm about ready done. Okay.
Is inflation used to solve current expanding universe?
Say that again?
Is inflation being used to solve current expanding universe problems?
No. Inflation was a brief fraction of a second, very early, right after the Big Bang itself, that then stopped. So subsequent expansion is not inflation, no. Multiverse would say it's still going on out there in all those other universes, spawning new ones. I mean, several billion more since you asked your question. But of course, they're all beyond our perception. In this universe, no, inflation is over.